welcome to the St Andrews Union Debating Society, the oldest and some might say finest of its kind. Thank you very much. We have a fantastic debate for you this evening. This house believes that maths is fake. Or this house, oh goodness, I've forgotten the long title already. We are joined by some excellent speakers tonight. Greg Restall and Dr. David Waszek on the proposition. And Pedriali and Peter Cameron on the opposition. Before we begin the debate this evening, I would like to invite the clerk to read last week's minutes in the style of Albert Einstein.
Thank you, Mr. Speaker, and I've got to admit that I wasn't here last week. And in the words of Albert Einstein, as far as the propositions of mathematics refer to reality, they are not certain, and as far as they are certain, they do not refer to reality. And in that essence, Mr. Speaker, I can neither find nor am able to read last week's minutes.
Goodness, there seems to be some existential confusion in the House. We will have to take a vote by oral acclamation. All those in favour of taking the minutes as read say aye.
Aye.
And all those against say nay.
Nay.
It seems rather close. I will have to consult with my sergeant.
Aye.
The minutes are taken as read.
Aye.
Without any further ado, I give the call to the first proposition speaker to begin the debate tonight, defending the motion that stands in their name. Hear, hear.
Thank you very much. So I want to start this off by stating unequivocally that mathematics is not fake. The only fake thing is this version of the proposition. The real question, the genuine question before us, is mathematics discovered or invented? And just as unequivocally, I will defend that it is invented. So to warm us up, let's think in general about what we mean when we say that something is invented. What are iconic prototypical inventions? You might think of the Wright brothers' aeroplane, you might be thinking of the electric light bulb with a filament. In France, where I'm from, there is every year a competition for inventors. One of the recent winners, for instance, was a very ingenious device for visually impaired or blind people that takes a camera, video image from a camera, processes it, and then transforms it into haptic feedback on the person's back as a visual representation, as a representation of the scene. It's not quite visual anymore. Now, if you reflect on those examples, you will see that none of these are arbitrarily made up. None of these are made up in a flight of fancy without any constraints. They are constraints in many ways. For instance, fluid dynamics will constrain the design of an aeroplane, and yet there are many ways you could build an airplane. You could have a V-shaped wing, or you could have a tube with wings, as we're used to. There are many ways to go, and not a single one. So in all of these cases, what we have is a clever design within and around constraints that is fit for some purpose, or that is designed to serve some purpose. By contrast, what would we call discovered? Well, if I were to go in the basement and dig and find, I don't know, a sword, a Viking sword, let's say, I might say I've discovered the sword. Or you might say that Mary Skłodowska-Curie discovered the chemical element radium. There are some complications in the second example, but let's leave them aside for tonight. Now, let's return to mathematics. Is mathematics more like the Viking sword, or is it more like the clever haptic feedback device that we discussed. In other words, is it invented or is it discovered? I think that it is very clear that it is in the sense that it is made up of a system of objects and practices that are designed for some purposes in certain contexts. It is not just a domain of objects out there like numbers or sets that we would discover and whose properties we would investigate and then discover. To convince you of this, I want to take an example, and not an exotic cherry-picked example, but a very central one that would be encountered by any undergraduate in mathematics, namely what we call the real numbers, which one might argue are anything but real. What are the real numbers? So the real numbers include the integers, 1, 2, 3, 4, also negative, -1, -2, fractions, 1/2, 2/3, -3/4, but also square roots, for instance, square root of 2, further roots, and more exotic numbers such as pi or e, and also many numbers, most in fact, which have no name and indeed could not have a name because there are too many of them. I'll come back to this. One of the primary purposes of the real number is to allow us to describe continuous phenomena in the world, for instance, the continuous motion of an object. The idea is that we can imagine the motion of an object as going through an infinity of points, many of which are too close to one another for us to be able to distinguish them by measurements. So we're fictionally, if you wish, imagining this infinity of points that the movement goes through. Now, how do we define the real numbers? We might say that, to make it simple, that a real number will be defined as an infinite sequence of increasingly close measurements, if you would like. So an infinite series of arbitrary measurements that are getting closer and closer to one another. And then you might define the set of real numbers to be the set of all these possible sequences of measurements. Now, if you look more precisely into the way this is done in an undergraduate course, this is quite archaic and complicated. Usually, you would define these, as I said, using sets, the sets of those measurements, which you could imagine as fractions, arbitrary sets. What are sets? Well, sets are defined in a very Byzantine and complicated way in what we usually call Zermelo-Fraenkel set theory with the action of choice. There's nothing obvious about this at all. In fact, if our goal is to describe, model, come to grips with continuous phenomena in nature, there are other ways we could have gone, and there are other ways we have indeed gone. One of the founders of calculus, Leibniz in the 17th century, initially worked with continua using infinitesimal numbers, infinitely small numbers, and then a whole hierarchy of infinite numbers that are infinitely small with respect to numbers that are infinitely small and also infinitely large numbers. And in fact, there are ways of manipulating such entities in a perfectly reliable and rigorous manner. In the 20th century, there have been various ways of making that kind of procedure more rigorous, if you'd like, using what's called non-standard analysis, also in various variants, including in so-called internal set theory, that allows you to speak rigorously about what it means to be infinitely small with respect to something you can measure. And you can, in fact, handle continuous phenomena in this way. In fact, there are textbooks that have been written of the calculus that are based on this way of proceeding. Again, this means the so-called real numbers are not just out there the only way of handling continuous phenomena. Depending on our purposes, the kinds of modeling we want to do, the kind of theory we want to be working on, there are various ways of approaching this question. And we can build various systems of objects to do that. The real numbers are just one possibility among many. this should remind you of what we said at the beginning about invention. This is prototypically the kind of thing we would call an invention. Now, you might think this is just one way of approaching the issue, but perhaps there are objects that are in some sense, in mathematics, that are in some sense unavoidable, that you will have to come up with. Perhaps with the concept of group, for instance, we have captured any reasonable way of describing a system that's invariant under certain symmetries. Perhaps you might think we have captured the essence of what it means to have a space where you can talk about objects being close to one another with the concept of a topological space. But even those could still be up for grabs. In fact, one contemporary research program in pure mathematics starts from the premise that for some of the purposes that we're pursuing in mathematical research, topological spaces are no longer fit for purpose. They do not serve our needs in the best way. And it has been proposed to replace them by an extremely complicated contraption called condensed sets. Now, you might answer, well, but what about, let's say, your favorite theorem of the calculus, let's say the mean value theorem? Is that not discovered rather than invented, at least once you've set up calculus in a certain way? Well, perhaps. But the question is not about your favorite theorem. The question is whether mathematics, as we know it, as it is taught in an undergraduate degree, is invented or discovered, so the calculus as a whole. And here, it seems clear to me that the right answer is to say that it is invented and not discovered. Thank you very much for your attention.
I thank the speaker for their excellent address, and now cross the floor and give the call to the first opposition speaker to begin the case for opposition bench. Hear, hear.
It's a little known fact that Sherlock Holmes had a sister. It's really little known because it is not a fact at all. If we take the Conan Doyle stories about Holmes as a kind of theory, you can say that it is not system complete. It doesn't decide a sentence Sherlock Holmes has got a sister. The sentence doesn't have a truth value. So how can we decide this sentence? The sentence is undecidable, right? How can we decide this sentence? Well, you know, we can dig, not in the basement, but in Conan Doyle's archives. We may find a scrap where he says, oh yes, Holmes had a sister called Elspeth, right? The point is that the truth maker, if we find one, will be a clear case of human invention. So it is Conan Doyle deciding, stipulating that Holmes has to have a sister. This is a clear case of human invention. Our opposition, they call themselves proposition. They are the opposition to something which is so clearly and obviously true that mathematics is discovered and not invented. Our opposition wants to claim that in mathematics we settle undecidable questions exactly in the way in which we can settle questions about Holmes' sister, right? And that's obviously ridiculous, right? So let me try to convince you of that. But first, something that David was saying at the end, we must be clear about what we mean when we say that it is invented or discovered. So what exactly are we talking about? So here is an example. A mathematician called Leopold Honecker said, God has given us the integers, all the rest is the work of man. Right? So here there is a claim that the numbers were not invented. What we did with them, including construction of the reals, is our work. Right? Here is a different case. Take chess. The game of chess is something that we clearly have invented. We know the history, how we developed it. So we've got the pieces, the chessboard, and the like. Here is Kasparov in 1999 playing Topalov. The crux of the game, a move that astonishes the audience. It is considered the best game ever played. And people claim that you can only explain a move by saying that Kasparov could see 20 moves ahead. You have the kind of depth or see or something. Now, chess is very interesting, mathematically speaking, and you can say we invented the pieces, but then the kind of logical space of the chessboard, the number of combinations, there are more combinations on a chessboard than there are particles in the universe, by the way. And the mathematics is mind-boggling. So here's a case where we invented we invented the chess pieces, but then settling questions about chess problems is well beyond what we can call an invention. We discover combinations. We discover whether there is checkmate in 30 moves or whatever. So what I'm trying to get you to kind of agree is that the dividing line between invention and discovery is not clear at all, but also we must be clear about what we are talking about, whether we're talking about inventing the building blocks or inventing the whole thing, the structures, the objects, in a very complex sense. And now let me go back to aspects of mathematics and the plausibility that we might think of mathematics as an invention. So there are undecidable questions in mathematics, in set theory and the like. Usually we take undecidable questions to be system relative. The idea is that you make a system more powerful and you settle questions that are undecidable. But the question that Gödel raised was whether there are absolutely undecidable questions. So questions that no system could ever settle. And the point is that it seems there is a lot of debate whether or not there are, people take different views, but the idea is that if there are absolutely undecidable questions, they are not a matter of stipulation. So we may find a proof, but the proof is mapping, is discovering a territory which is out there. And let me close by saying something about one of the reasons why people have been inclined to think of mathematics as invented, and it's not a particularly respectable book. It's a book called Where Mathematics Comes From by Lakov and Nunez, and they claim that it's a matter of our concerns, that mathematics reflects a certain ability to use conceptual metaphors, and that kind of consideration. But now here's the thing. We got mathematical knowledge about any number of things, right? And we got what we know about our human mind and the like. Now, I ask you to consider the scenario in which we change features of our cognitive makeup. We change features about our concerns, our interests. Now, the opposition, or the proposition, depending on the view, is asking us to believe that any changes that we make to our interests, our concerns, our activities should make a difference to what is true in the mathematical domain. And I'm sorry, that's something that I will never buy to my dying day. Nothing that changes on this side will affect what is true in the mathematical domain. And I put forward the proposition that mathematics is discovered and not. Thank you very much.
To concede that there are so many discoveries in the wonderful world of mathematics, that there are wonderful mathematical discoveries that we have learned through the centuries, but I must remind everyone here that the question that's at issue is not that mathematical discoveries aren't made, but whether mathematics as an edifice, as mathematics as a discipline, mathematics as a practice, is an invention or a discovery, and the answer to that question is easy. I'll consider the analogy of chess that Walter introduced very, very helpfully for us. In the case of chess, it is absolutely true that there are discoveries, that we make discoveries about chess. that we make discoveries about when it's possible to do a checkmate with various combinations of moves and when not. But nobody, when they say that, when they make that conclusion, therefore thinks that chess is a discovery. Chess is a human invention, is a human construction. But it's not just because of games or fictions or things like this that human inventiveness comes. Take instead the example of physics. I mean, in physics, we learn about our physical world by the use of different concepts, by the application of measurement, by the theorizing and the development of different theories. Nobody would say that it's up to us completely, and that it's purely just a matter of fictional choice about one option or another as to what physical theory that you might choose. But nobody also will say that the theories of physics themselves are just purely discovered. I mean, if I could just dig up a theory of physics and discover it, then we wouldn't need to be making particle accelerators or funding physics departments or things like that. Neither chess nor physics are, discoveries themselves, even though they're filled with discoveries. So mathematics, as a practice, as a body of theory, is filled with the results of human ingenuity, creativity, construction, and obviously inventiveness. Now, to build on my colleague David's examples and arguments, I'm going to show that mathematics is a human invention by way of just doing a little tiny bit of philosophical analysis and showing that mathematics bears all of the marks of a human invention. Inventions are characteristically involve a sense of arbitrariness. There's choice. There's cultural relativity. Different people do things different ways. Different people, inventions in one part of the world are not the same as inventions in another part of the world. Inventions are also, in some sense, open-ended. They never, when somebody's invented something, that's not the end of the matter. There's more than one way that things can be done and can go on. And inventions, as we've already said, are purposive, whether they're to solve a problem or whether they're to express a view or whether they are just to create something beautiful. Inventions are made for a purpose. It'll be easy for us to see that all of these three different marks are shown by mathematics as a technique. Mathematics is the kind of thing that you either love or hate. I mean, you all love it. I mean, mathematics is wonderful. So let's go through these examples. First, it's obvious that there are different cultural and historical and traditional differences between ways that mathematics is done. There are different accounts of what the real numbers are. There's different accounts of measuring space and all of that. I'm not going to go into that example anymore. Let's consider instead the way that mathematics is done for some point. Mathematical theories are the kinds of things that we not only develop to describe the world in various ways, whether it's to measure or count or do all of the different things that mathematics is applied to. It's also expressed, it's also explored because of the beauty that's involved in the development of mathematical theories. It's something which has got its own aesthetic qualities. All of these things aren't to deny the fact that mathematics is an invention, but confirm the fact that mathematics is an invention. But the thing that I'm going to spend most time on is the idea that mathematics is open-ended. Because on that point, the open-endedness of mathematical ideas is an illustration of the fact that mathematics, again, as a theory, as a practice, is a matter of human action, of human invention. We've already talked about the notion of number. But the notion of number is not an all one and done thing. It's not just that there are whole numbers. We've already talked about the difference between integers and real numbers, but to add to that, there's complex numbers, there's quaternions, there's ordinal numbers, there's cardinal numbers. The notion of a number has been expanded again and again as mathematicians have gone on to consider different ways of thinking about what it might be to count or to measure or to do these things. This is an open textured concept, the philosophers say. It's one that, as it's developed, as we use it, we can go on and develop it more by our inventiveness. But let me think of a more challenging example that was actually broached by Walter. The notion even of the simple mathematical concept of a set. This notion is open-ended in a whole bunch of ways. It's not only the sense of when you've got sets of things, then you have sets of things, and sets of sets of things, and things like that. You might wonder, how far does it go? Yeah, that's a question. How far does it go? How many ways can you nest that? But it's open-ended in even a more deeper way. Now, is everybody familiar here with what a counting number is? You know, things like 0, 1, 2, 3. You all got that idea?
Yep.
I thought you'd be a more responsive audience. My goodness. Well, do you know how many numbers there are? How many of those whole numbers there are? The technical word for it is there's a lot of them. There's a lot of those whole counting numbers. It turns out that we can make different sets of those numbers. There's like the even numbers, the odd numbers, the prime numbers, there's your favorite numbers, there's a whole bunch of different sets of numbers, right? There's probably a lot of those sets of numbers too. Okay? Now, it's a nice mathematical result that if I had a whiteboard here we might go through, which is the idea that, in a really important sense, that there is more sets of numbers than there are numbers. You can't pair them up one-to-one in any way. And that's an amazing mathematical result. But an even more amazing mathematical result that Gale Cantor, who proved this result, asked himself is there a set of numbers, is there a set of anything, a set of whatever, that is bigger than the set of numbers, but smaller than the set of sets of numbers? And it turns out that the answer to that question is one of these questions that Walter was talking about. That is absolutely undecidable in some sense, at least given the concept of set as we know it. And this, the mathematicians that I try and understand, because I'm not a mathematician, I'm just a philosopher and magician that tries to understand a little bit about how mathematics works, the logician Paul Cohen in 1963 showed that the standard view of the concept of set that we have used does not settle that question one way or another. Now, that fact does not mean that settling the thing is a matter of arbitrary human choice. We're not, those of us that say that mathematics is an invention and not a discovery, are not saying that it's only like absolutely arbitrary fiction. What we are saying, though, is that it's an open-ended, the notion of set is an open-ended concept that we could develop in various ways, but we're not really sure what the constraints of the exercise are, because as a human practice, there are things that we are doing, there's things that our concepts mean that we also, discover, but it's because they're our concepts in the way that we are using them that we can discover more about. Just like chess. I mean, chess is repeat after me, chess is it a discovery or an invention? Chess is an invention. Have discovered chess. The human race invented it. And then other people discover it. So, let me conclude. Mathematics is essentially open-ended, mathematics is made for a purpose, and mathematics is filled in a wonderful way with arbitrary choices and cultural differences. That doesn't mean that whether or not something is a mathematical fact is arbitrary, but the choice of this mathematical fact or that mathematical fact and the kinds of things that we can express is. So I submit to you then that since mathematics looks like a duck, quacks like a duck, swims like a duck, or is arbitrary, is open-ended, and it's for a purpose, means that it has all of the features of this wonderful invention, this glorious and maddening invention that is mathematics. Thank you.
I thank the speaker for their excellent address, and now we cross the floor and give the call to the second opposition speaker to continue the case for opposition bench. Here.
Well, thank you. Is mathematics discovered or invented? if I were really wanting to answer that question, with all due respect to my colleagues on both sides, I would not ask a philosopher. I would look at what mathematics actually is, what mathematicians do, and pin my argument on that. And that's what I propose to do for you. But just before I do, let me say a little bit about the difference between discovery and invention, because mathematics is not discovered in the way that, say, the Viking sword in the basement was discovered. But I believe you can think of it like this. I understand that there were valleys in the Himalayas from which the people who lived there could see a big mountain, and they were all convinced that all these mountains were different until they discovered that they were all the same. I count that as a genuine discovery. They were all given different names and regarded as being different mountains, but they were all the same. Now, what I propose to give you, this is perhaps a little bit dangerous, but to give you two actual pieces of mathematics which have threads running through the whole body of mathematics in a way that could not have been invented, because if it had been invented, the different inventions could not possibly fit together quite so well. So let me try and do that for you. So the first one has to do with symmetry. We've had mentions of symmetry already. Symmetry is a thing, there's no doubt about that. When you look in the mirror in the morning to shave or put on your makeup or whatever you do when you look in the mirror, you're using symmetry. Symmetry is used by physicists to describe the elementary particles that the world is built out of. Now, mathematics have made symmetry into a subject that's called group theory. And in the 19th century, mathematicians discovered that at least for finite groups, they're built out of certain atoms which got the name of finite simple groups. In the 20th century, mathematicians discovered all these atoms, all these simple groups, though they didn't know that they'd got more until this century. But they form an interesting collection. There are a certain number of infinite families of them, and then there are just 26 odd ones out, the sporadic simple groups, so-called, which don't fit into any of these patterns. The largest of these sporadic simple groups has order more than 10 to the 50th power. That's quite a big number, but not that big. It's not as big as the number of particles in the universe, for example. So we can just about get our heads around it. But in the early days, when this discovery had not been completely made, the mountain had been glimpsed, but was still shrouded in mist. A couple of things were known about this group. First of all, its order. I haven't given you the exact number, but it was known exactly. The second is that if you want to represent this group by matrices, now we all love matrices, don't we? The size of the matrices that you would need would be 196,883. Those are quite big matrices. Imagine a spreadsheet with 196,000 rows and 196,000 columns. In that spreadsheet, you can put just one element of this group. Anyway, this came to the attention of John Mackay, a British mathematician working in Canada. He was one of those people who had a wide knowledge of mathematics. And in particular, he knew about an entirely different branch of mathematics, complex analysis, that had been developed in the 19th century. And one of the things they found was a function called the modular function, or sometimes called the J function. This is a function which in some sense takes the complex numbers, which are like a plane extending to infinity, and picks out the counting numbers, the integers. That just points along a line. It somehow identifies them. And because it identifies them, you can shift it one place to the right without changing it. And from a piece of mathematics that was already well known, this means that you can represent this function by a certain kind of series called the Fourier series. And when you do that, the first coefficient is 1, second coefficient is 0, Third coefficient is 196,884. One more than the number, the size of the matrices that represents the monster. John Conway, who was one of the most inventive mathematicians of the 20th century, learned of this discovery and described it as moonshine. And if mathematics were invented, Conway would have been absolutely correct. But he was completely wrong. There was a deep theory lurking behind that simple observation, which has been developed, things have been proved. We don't understand everything, but at least the main results, infinitely many equations like the one that I just gave you, have been proved. And this subject is now called monstrous moonshine. Conway invented the name monster for this group. It was previously called the friendly giant because it had such beautiful properties and because it was discovered by two people, Fisher and Grice, so it commemorated their initials. But, so this is, the term monstrous moonshine is a bit like the Big Bang. It was invented as a derogatory term, but it's been taken up with pride, and monstrous moonshine is now a subject. But it links together these entirely different parts of mathematics. And Mackay was probably one of the few people at the time who knew both of those areas and could make that connection. So let me get on to the second one. So Alan Watts, who was a writer and a Buddhist philosopher, classified people's views of the universe into what he called prickles and goo, or in slightly more formal terms, discrete and continuous, right? And so some people look at the universe in one way, like, well, these go right back, the pre-Socratic philosophers, the atomists had a prickly view of the universe, whereas Parmenides and Zeno had a gooey version of the universe. Then John Maynard Smith, a mathematical biologist, looked at this and said, nowadays we have a method of changing. He didn't say goo into prickles. He said quantity into quality, and so it was quite clear what side he was on. If you look at your body, it looks pretty much like goo, doesn't it? But we know now that the secret of life is prickles. It's the genetic code, which is a long sequence from a 4-letter alphabet. So now we have a method of turning goo into prickles. And about 50 years ago, there was a subject that was very fashionable at the time. It had the dramatic name catastrophe theory, or again, slightly more formally, singularity theory. And people worked out 7 different kinds of catastrophe, which might explain natural processes where discrete results come out of continuous causes. Then along came the Russian mathematician Vladimir Arnold, and he said, there aren't 7, there are infinitely many, and they're described by some nice diagrams. You probably can't see this, but on the front of this book, there are some diagrams, 2 infinite families and 3 sporadic ones. So one is just endpoints in a line, that's called AN. One's like that, but it forks at the end, that's DN. And then there's E6, E7, and E8. And Arnold observed, so those diagrams date from the early 20th century in a classification of things called Lie algebras, which are useful in physics. But he said, all over mathematics, you find these ADE diagrams. The subject is just riddled with them. So the singularity theory, the representation theory, graph theory, general relativity, all these things come up in all those different areas. And one of the authors of this book, John Mackay, the same John Mackay, noticed a connection which has the regular polyhedra on one side. You know about the regular polyhedra, tetrahedron, the cube, all those others, 5 of them altogether. But they come in 3 pairs. The tetrahedron counts twice. Then there's the cube and the octahedron, the icosahedron and the dodecahedron. Those 3 pairs in Mackay's correspondence correspond to the E6, E7 and the E8 diagrams. And so they give you we heard about the complex numbers, the quaternions. There's another step, the octonions, and these things might be involved in the theory of everything. No one's quite sure yet. But so John Mackay and his postdoc, Yang Hui He, were writing a book about it. John died a couple of years ago, so Yang had to find other people to help him finish the book. And he rounded up two people, Philippe Deschamps and me. Philippe had observed that a lot of microorganisms, like viruses, form in the shape of regular polyhedra. I had come across it in a different way. How much time do I have? 1 minute. Okay, so just very briefly tell you a story about how I got to get my name on the front of this book. So I was doing some research with two colleagues, one in the Netherlands, one in Belgium. I went to visit the Dutch, we were trying to get a classification for a certain class of graphs, which I won't tell you any more about. But they reduced it to a geometric problem. If you could solve the geometric problem, that wouldn't solve the whole thing, but it would at least give you a big shovel on the way. So I visited the Dutch colleague and he said, I've solved the geometric problem. There's one infinite family and 3 sporadic examples. So he was going to explain to me the next day. The next day we drove down to Brussels to visit our other collaborator who said, I've solved the problem. There's one infinite family and 3 examples. And when they compared notes, each of them had missed out 1 infinite family. So there were 2 infinite families and 3 sporadic ones. And it was the ADE pattern. Now, even this was before Arnold made his observation. But I realized it was ADE, and as soon as it was, the whole thing became simple and beautiful and clear, and we had the result. So these threads going through the whole of mathematics surely could not have been invented, because the inventions would never be so coherent. Thank you.
Everybody in attendance has the opportunity to give a speech of up to 1 minute in length. It looks like we have time for about 7 speeches or so. If you would like to make a speech, please raise your hand nice and high so that I can see it and point to you. We did have a microphone, but it might be a bit of a faff, so please project your voice nice and clearly. And before you give your speech, if you would like your name to be included in our minutes book, which goes back almost 200 years, or over 200 years in fact, then please state your name nice and clearly before your speech so we can put your name down in front of your contribution. So do we have any speeches from the floor? Yes.
Thank you. For the minutes, I'm Susan, and I'm not a mathematician, so I might mess some things up, but I am into philosophy and language, so that's mostly what I'm going to talk about. I'm going to look at my phone because I have it written down. So we have different languages to describe the same things. If P and Q, then P. Martha and Jonas exist. 1 + 1 = 2. These are all mathematical statements in the fundamental sense of what mathematics is. That is, a language used to describe items and the relations of items between each other. So it lays on the foundation of object individuation, something that develops independently of the environment in all newborn children and other animals, such as rhesus monkeys and dogs. In all senses of the word, that means that it is innate. It's sort of a Platonian thing, but it's empirically true by psychology. This seems to suggest that while mathematics, the language, is invented, just like the language game in the Wittgensteinian sort of sense, mathematics, the objectively existing collection of truths, is inherent in logic and in human reason. So I may be mute and not able to name or describe a cup, but the cup still exists. If a tree falls in the mathematical forest and no one is there to hear it, it does still make a mathematical sound. So the two sides of this debate seem to be talking about 2 different things, a language and its subject. That is, to me, the main disagreement.
David Kearns for the minutes. I'd like to build on the point that's just been made about the distinction between mathematics itself and our representation of mathematics. I think that distinction is what the proposition has been missing in this debate. And I would argue that while our representation of maths might be an invention, the maths itself is objectively true. And evidence for that, in my mind, is that maths works in practice. There was probably maths involved in making this building. And here it is standing, it's not fallen down, the maths has worked. I can't see how that would be the case if it were an invention. The proposition might counter this by saying, well, there are inventions such as the invention of a new medicine that work in practice. But I would say that the medicine itself, as the pharmaceutical product that is sold, might be an invention, but the chemical reactions that are happening to destroy the pathogens in our body, those are real. Those have been discovered by the people who have invented medicine. Therefore, I agree with the opposition that mathematics has been discovered, not invented.
Do we have any further speeches from the floor? Yes.
But if you didn't like the philosophers talking about maths, you would definitely not like the historians, but here we are. Well, the way that history loves to conceptualize this is that, essentially, if you take physics today, or more what's usually used as an example, chemistry today and 500 years ago, you're not talking the same language. If you take a chemist from 500 years ago and plant him today, he will not understand a thing. You're not literally talking the same language. Same with history. Historians today do not write the same kind of history that they wrote 500, 1,000 years ago. So the problem with maths is that essentially it is something that is a relatively constant. So essentially what I want to hear from both sides is, can you prove a relative continuity? Because also maths is about practice. So all of the theorems that have been disproved, altered, the developments have, for example, the disproved stuff been put to practice and did they work? Did they not work? And they were changed. It is this sort of continuity that we need to see in the historical context, if you will, to see whether or not it is in fact an invention or a discovery. Because, okay, fine, yes, the cat down the street will not use math. Math as a language is a human invention. But essentially that is what, in the historical mindset, makes the difference of, can we see some sort of continuity? Or at the end of the day, the mathematician of 1,000 years down the road will see today and will see something completely different. Thank you very much.
Do we have any further speeches from the floor? I realize there's nothing on this side of the room. There we go, fantastic.
For the minutes, my name is Nicholas. This is a question specifically for people that believe that maths is invented instead of discovered. And it's building on a previous point that was brought up, which is that maths seems to be across species intuitionistic. Humans are not the only species capable of performing simple mathematics like arithmetic. We have animals that are more than capable of being trained to do things like addition, subtraction, multiplication. They're even able to gather, more difficult forms of mathematics, something that calculus was discussed earlier for do birds perform calculus when planning flight plans. While the language, like we talked about before, was man-made, while calculus is something that we can think of, the same thing was being performed, like that string between each independent object, where they're able to get from one place to another in practice, just like the building stands. I wanted that perhaps addressed.
Further speeches from the floor. We probably have time for 3 more, and I see 3 hands. Oh, I see more than 3 hands now. Okay, I will go with the ones I saw first. I'm afraid there might not be time for every speech, but we'll get on to what we can do about that later. Yes.
I'm going to say what the speakers before me have said, but far less eloquently. I think everyone here knows what discovered means, and everyone here knows what invented means, but I'm not sure everyone here knows what mathematics means. I think that's the hardest term in this argument to define, and I think you're arguing two different arguments, 2 different points, 2 different problems. Maths as numbers, as fields and planes and the universe is a different thing to the language that we use to describe that mathematics. And I think the issue here is that you are both talking about different definitions of the word mathematics.
I think I'd like to answer the points about practical applications. Is that there are some concepts in science, like for instance ideal gas, idealizations, which do not really exist in nature, yet they work when being practically applied, like there are satellites using electrical propulsion in gas. And so I would say mathematics may be something like this. It's incredibly useful idealization which we cannot discover from the nature, from any empirical data that's available to us, but it works very well. And regarding intuitions, I think in this case you were naming intuitions as not something, unified psychological faculty, but it's just various processes like memorization, like linguistic inference, which we call intuition. But I think to a person who is unexperienced with math, for me, for instance, it's definitely not intuitive that 2 + 2 = 4. It's something that I learned in high school here as well. But I wouldn't say that mathematics as an idealization is something that can be clearly intuitive from the, from our cognition or from the world that we have. So yeah, that's my point.
I'm in my final year of a maths degree, so I don't know whether I'm kind of coming at it from a different perspective to a lot of people. But I think there's a lot to be said for the fact that, as many people have agreed, that the language of maths is somewhat arbitrary, and we've kind of decided what axioms we're going to take to be true, because there's no way that we can prove those outside of our system of knowledge. But then the fundamental facts that we find as a result of that are discovered based on our assumptions of what was true. I think to come back to Professor Cameron's example about group theory, for instance, we define what the object of a group is, and then any results that we find are based on that definition, but they follow quite naturally. So it feels like we're kind of discovering things from the starting framework that we have, but then I would argue that for any discovery that there is out there, there's got to be some kind of framework to start from before you get to that discovery.
Thank you, everybody. I'm afraid that is all the time for contributions that we have at this portion of the evening. So it is now time to bring the debate back to the dispatch boxes. Each bench has a total of 10 minutes to give their reply. And so I give the call to the opposition bench to begin their reply. 5 and 5?
Okay, fine.
All right. Thank you very much.
Well, yes, several of you have made the very good point that there's a difference between mathematics and the language of mathematics. So I mentioned John Conway earlier on. One of the last things that Conway wrote before he died was a plea for a mathematician's liberation movement. We shouldn't have to make all these overly complicated definitions. We should be able to just say what we want the object to do and have some guarantee that it does it. Well, we don't have such a thing at the moment, but that is perhaps the ideal, and that would essentially get rid of this dilemma, because the language wouldn't be so important then. You can talk about the real numbers in many ways, as limits of sequences or as cuts of the rationals and all kinds of things. But in Conway's view, you should say what you want the real numbers to do, and then it will follow from that there will be real numbers that do it. We're not there yet, but that might be the thing that we're heading for in that direction. So I'll leave it there.
So I've got a few bones to pick with my colleague, Professor of Mathematics. So to begin with, you had a bit of a sleight of hand. The point was about invention. Invention has to do with what is invented. And you smuggled in inventiveness, which is a completely different approach. So if there is inventiveness, that is compatible with discovery. Many discoveries display a great deal of inventiveness. So that was the first point. I thought it was a cheap shot. So, anyway, the other thing is about understanding and history of concepts. Because it seems that you put all this circumstantial evidence for your main proposition. And one was, oh, we change our mind about stuff. Change our mind about the fundamental concept of mathematics or set theory, right? So the idea that Cohen showed that there is something indeterminate about the concept of set, he did no such thing. He showed that our understanding of the concept is incomplete. He showed that there is a history of our grasp for the concept, but it doesn't follow from the fact that we fumble in the dark trying to understand the fundamental concepts of mathematics, that those concepts themselves are indeterminate. It may be that they are, but it doesn't follow from the fact that we struggle. And in fact, the fact that we struggle to understand those notions shows an analogy with discovery, because exactly the same thing goes on with the fundamental notion of science, as many of our friends have pointed out. Right? So that was the other point that I wanted to make. Final point, I suppose I should say that I think mathematics is absolutely everywhere, so chance is discovered, because again, we happen to have a history of how we got to that kind of world of possible combinations. But the fact is that mathematical structures are absolutely everywhere. They permeate absolutely everywhere. And on the point that someone has made, that the main argument that he can give in favor of the kind of objectivity of mathematics and the fact that it is discovered is the applicability of mathematics. There I think we must be a little careful, because some people made the point that it seems as if it is unreasonably effective mathematics. It's so pervasive, and then you may think, oh well, it has got to do with our brain. We decode the world because of our cognitive apparatus. No wonder mathematics fits everything, because it simply projects our biases. Right? And so I think we must be careful. Applicability is probably the miracle argument that has been given. It would be a miracle, pretty much what Peter was showing. It would be a miracle if there were these coincidences across mathematical structures. But I think let's use that argument, but let's be careful not to prove too much, because then we make it go in the way of the proposition, and I would really be very disappointed if anything I said would move the board in that direction.
And cross the floor and give the call to the proposition bench to conclude the debate this evening. Hear, hear.
Well, let me first reiterate that none of us here on the proposition side is denying that there are discoveries in mathematics, that we discover some things, for instance, the monstrous moonshine phenomenon. Once, as the last student, I think the last student said, once we set up some elements of our framework, some things we will discover within this framework. Now, the question that the monstrous moonshine phenomenon raises, what is it exactly? Does it mean, is the question, well, where does this phenomenon come from? Does it show that our framework is the right one, that we are asking the right questions, that we have the right objects? Is that what we're supposed to take away from it? I think that's too quick, and maybe we should be wondering about why we are investigating this particular area of mathematics, why we are pursuing this kind of research that we are pursuing. And maybe part of the answer is that we are designing our mathematics also to be a structure that is rich, that we can engage with in a rich, open-ended way that allows for a lot of ingenuity as a collective human endeavor. That's also on top of its role in allowing us to better describe the world. On top of that, it's not clear what individual instances of connections throughout the whole of mathematics are supposed to show about the basic way of practicing mathematics that we have. What I do want to speak against is this idea of the distinction between the language of mathematics and mathematics. I don't think, or the representations of mathematics and mathematics, I don't think there's a unique mathematical world that we're describing. If we have different ways of talking about continua, maybe we have the real numbers as we know them on one side, and maybe on another side we will just want to speak about what we can compute by way of an algorithm, for instance. And then we have many fewer real numbers than the real numbers we're used to, and the same theorems might not be true any longer. For instance, perhaps the intermediate value theorem is not true in the same sense as it was true before. I don't think there's a single reality and we're just trying to describe it. There are different ways, different frameworks that do not actually agree with one another to do certain tasks designed for certain purposes. For instance, the purpose of helping us tackle continuous phenomena in the world, phenomena at least that appear continuous to us, because who knows whether the whole of reality should ultimately be described in discrete terms. Now, one final point I would like to address is the point that was raised about the history of mathematics in the front row, as I would consider myself a historian of mathematics. What about continuity? If we have all these different practices, how come they might seem to all agree or to be describing the same results in a certain sense? Is that true? Well, certainly within each practice, certain things are determined, and certainly there are relations between the practices. But whether we consider that in fact they are all proving the same theorems is partly a matter of choice and about how we describe the history of mathematics and how we write it. So for instance, as I said, there could be different ways of approaching continua and we might not have the same theorems. That's one case in which things do not agree. But then what about ancient geometry versus contemporary geometry? Is it the same theorem we find in Euclid to the one we could prove in an undergraduate textbook today? Well, this question is underdetermined because the text as we find it in the sources does not fully determine questions that we might want to ask of it from a contemporary perspective. For instance, are continuity assumptions sufficiently taken account of in the Greek source? In fact, we could either say, oh, this ancient source is flawed, it is wrong, it fails to prove the theorems we're interested in. Or we could say, oh, the theorem is correct, everything in this book is correct, we just need to read it in the right way. We just need to add assumptions in the right places that maybe people back then were not fully aware of, and then we will realize that, in fact, the results are the same. This is a choice that we have to make. It is not obvious which way we should make it. Thank you.
Respond to Walter's pointing out that the word inventiveness and the word invention are clearly not the same word, obviously. However, when somebody acts inventively in, say, proving a mathematical result, then that proof that they give is an invention. It's something they come up with, the connection. Now, it is also a discovery. I'm not denying that the proof is a discovery. I'm not denying that mathematics is objectively true, any more than the facts about chess are objectively true. But again, repeat after me, nobody would say that chess itself as a practice is well, nobody reasonable. That chess was not in the basket of wonderful human inventions. Now, on the point which I thought was really wonderful in Peter's explanation of the connections between the classification of the finite set of groups and other mathematics that I know nothing about. Yes, there are so many results where there are these threads that have been going for many centuries or decades of theorizing that do seem surprisingly connected. And I think I've got Professor Cameron's wording right. The threads that occurred through the history of mathematics could not have been invented because they would not have been so coherent if they were a human invention. And I agree. The claim that mathematics is an invention is not a claim that every part of mathematics is an invention. The fact that somebody built this building does not mean that somebody built every atom that's in the building. Of course not. Mathematics is an invention, but there are discoveries that are a part of it. In fact, we would expect that because humans have the concepts of counting and measuring and all of these different things which have got the structure that they have, we would expect that there would be surprising connections because they are things about patterns, but they are patterns in the concepts that we make. And we discover logically, indubitably, definitely, objectively, consequences of our own concepts. And so it's also not surprising that you would expect that other creatures can instantiate the same sort of things. Of course, but bird concepts of numbers, whatever they are, I don't know whether they're exactly the same as ours, but in our counting and theorizing about them, we will discover similarities because the whole point of numerical concepts is they can be applied everywhere in lots of different ways. But again, repeat after me, they're our concepts that we are applying. Now, it's true. When you get a mathematician, mathematicians really love mathematics, and that's true. That's one of the things that make them mathematicians. When mathematicians are thinking about mathematics, they're thinking about mathematics, and they are not thinking about mathematics. That's the curse of the philosopher. But mathematics is not numbers. Mathematics is how we learn about numbers. Somebody teaches you not just numbers, they teach you how to think about numbers. The theory is mathematics. And again, repeat after me, the mathematics is our mathematics. It's our concepts. It's the stuff that we do. And we discover new things in it all of the time. But that does not make it not a human invention. Okay? Let me see. There's a little bit, final point. Walter was saying that I said the co-enforcing argument was to be understood as saying that the concept of set is indeterminate. And I tried to be careful to not say that it said that. I did say that our current understanding of the concept of set is indeterminate. I agree. Now, it is true. We may discover that the concept of set does settle the continuum hypothesis in one way or another. But again, repeat after me, the concept of set that we discover these things about is our concept. It arises out of our practices of collecting things together and all of that sort of thing. The only way we have of doing this is by doing our reasoning and our thinking and our classifying and our thinking and cognizing about the world, and those things are the result of human activity. Yes, they are human activities, which is talking about the necessary patterns of the world, but that does not mean it's not our way of thinking about the necessary patterns of the world. And with that, it's something that we do. It's something that is part of our human capacities. It's something that does, yes, involve a heck of a lot of human inventiveness. Our ability to do this is ours, and it's something that we freely do. And for that reason, on this thing, yes, on this proposition, I can say nothing else than that mathematics, as the thing that you and I do, is a human invention. Thank you.
for what was undeniably a fine debate this evening. One more round of applause, please. It is now time to call the House to a vote. Now there are three options when you're voting. First for the proposition, then for the opposition, and then any abstentions. So, all those who side with the proposition and believe that mathematics is a human invention rather than a discovery, please raise your hand nice and high. Nice and high, please, sorry. And all those who side with the opposition. And any abstentions? Let them roll!
Shut up.
Before we have board announcements, I would like to extend a very warm thanks to our friends at SUMS, the St Andrews Mathematics Society. Not only did they single-handedly pretty much organize the debate this evening, they were certainly the easiest partners we've had to collaborate with all year, and I do believe they have an announcement, but first a quick round of applause for SUMS.
Just as a quick announcement, we still have some Pybalticus, so if you want to join us 14th of March, there are still some go get your tickets.
And do we have any announcements from board theatre maybe?
Yes. Thanks so much to our wonderful speakers. I think I don't understand anything of math. I'm very bad at it, but I really enjoyed this. It was one of my favorite debates this semester. If you would like to see more about debates, next week we'll be back at NPH, and we'll be doing. This house believes that relationships with AI should be normalized. So come along to this very fantastic thing.
Not to be able to make a floor speech, but I think Ariel has an announcement to remedy that.
Yes, if you guys want to keep talking about this, please come with us to main bar afterwards. It's open to both speakers and students to come further this conversation about maths and philosophy with a pint in hand. Thank you very much.
It is now time to announce the results of the debate. The ayes to the right are 72. The nays to the left are 104, with 21 abstentions. Therefore, the nays have it, the nays have